Hello, welcome to these 3 lectures on measure theory. We will briefly review Riemann integration and then go on to describe Lebesgue integration. I will not be proving anything. I will give an overview of Lebesgue measure and integration, which is an extension of Riemann integration. But without giving proofs of the theorem. So, there are 3 major theorems which I will state and we will see some examples at the end. Okay, so let me start with showing you the notes and then I will explain as we go along. Okay, so we have Riemann integration for bounded functions. So, boundedness is important here. F is a function defined in an interval AB taking values in the real line. So, we will stick to real valued functions. Okay, most of what I am saying can be done for complex valued functions as well. Now, you divide AB into several intervals, smaller intervals. So, I have if you look at the picture, you see how it is. The interval AB is divided into smaller intervals, and mi, small mi is the infimum of the function f in the interval ai to ai plus 1, and capital Mi is the supremum. So, both of these should be finite. So, that is where the boundedness matters, and then you form the lower sum and upper sum. So, lower sum is summation Mi into ai plus 1 minus ai. So, what is ai plus 1 minus ai? So, that is simply the length of the interval ai to ai plus 1, right. So, you are multiplying the infimum of f in an interval in times the length of the interval, and similarly for the upper sum is the supremum of f in an interval times the length of that interval. So, if you look at the picture, you will see the red lines denote the infimum of the function in that interval, and green ones give you the supremum, and multiplying the supremum or the infimum with the length of the interval will give you the area of that particular bar, right. As in the histogram, you have those bars, and lower sums will give you the area under the integral of the bars, right. So, it is a smaller portion than the area under the integral, and similarly the upper sum gives you the area of the bigger bars, right. So, when you sum up, you will get something more than the area under the integral, and we say f is Riemann integrable if you take the so let me go down a little bit. You take the limit of this upper sums and lower sums as mod p goes to 0. So, p is a partition, mod p is the supremum of the length of the intervals you have. Okay, if that goes to 0, and if these two lower sums and upper sums converge to the same value, then we say f is Riemann integrable, and we denote it by integral a to b f of x dx. Okay, so integral a to b f of x dx is a symbol which denotes the limit of either the lower sums or the upper sums. They should be equal for f to be Riemann integrable, and from the picture it is clear that it will converge to the area under the integral. Area under the curve. Okay, so that is why you say the Riemann integral is the area under the curve of or the graph of f. Okay, so let's continue. Now, in Riemann integration, what we did was to divide the domain of f into smaller intervals, and you formed these Riemann sums, upper sums or lower sums, and then looked at finer and finer divisions, right, finer and finer partitions, and then you take limit, and that is what you call Riemann integral. Lebesgue's idea. So, well, it was clear in the early or maybe late 19th century that Riemann integration was not enough to do a lot of analysis. because there were several functions which one could not integrate in the Riemann sense. Continuous functions are Riemann integrable. That's already a big class, but there were several other functions which analysts wanted to integrate, and that was not possible. So it was felt that it was necessary to extend the Riemann integration to various other class of functions, and that is where Lebeg's idea became crucial. So this was very early 20th century, so 1904. That's when Lebeg, I guess, published his paper. So Lebeg's idea fundamentally differed from Riemann's idea in looking at the range of the function instead of the domain of the function, and dividing the range of the function into smaller intervals, and then you take inverse image of those smaller intervals and associate a certain length to that set. So if I look at an interval I which is contained in the range of f, so if you look at the graph, you see that you look at inverse image of I. So inverse image of I is all those points x in the interval AB which is mapped into I. Okay, so it's not inverse as a function. Okay, so it's a map, inverse image of I is all those points x which are in the domain of f, which are mapped into I. Now f inverse of I in this this picture, f inverse of I will be a nice interval, but if I have a different kind of a function, f inverse of I need not be an interval. But then Lebeg's idea was to define a notion of length to these kind of sets. Okay, so let's try to understand that. So you go down a little bit. So define notion of length to all this f inverse of i's. So this length is the Lebeg measure m. Okay, we will denote it by m. If I have a suitable subset of the real line, I can define its Lebeg measure. We will come to that soon. And then Lebeg did exactly what Riemann did: choose some values in I and sum up as in the Riemann integration. So you have this f inverse. So if I1, I2, In, etc. partition range of f, and if you choose points x1 in I1, x2 in I2, etc., then you can consider a sum, summation xj. So in Riemann integration, xj was either the supremum or the infimum in certain interval, but that interval was in the domain. Here we are looking at the range and dividing the range into various intervals, and you choose these values xj and multiply by m of f inverse of ij. So I have not defined what is m. M is the measure or the length of the set f inverse ij. Of course, if f inverse ij is an interval, then the length is what you already know, right? If I have a interval AB, the length is b minus a, right? But there can be sets which are not intervals, like rationals, irrationals, or rationals contained in an interval like 0, 1, etc. Various kinds of sets, or disjoint union of intervals and so on. So one has to define length for such sets. Okay, if you can do that, you can form something like this, and then see what happens when the partitions become smaller and smaller. That was Lebeg's idea, and that became hugely successful, and it became extremely useful in developing analysis. Okay, so let's look at a very simple example before we formally define things. For example, consider a step function g. Okay, so I have this interval a to b, which I call a1, and divide to a1, a2, a3, a4, a5, and in each interval the function g is a constant. Such a function is called a step function. Okay, of course in this picture the function g is positive. It need not be, it can be any values. Okay, so in the first interval the value is alpha 1, second interval the value is alpha 2, and so on. Okay, so if I have a step function, then of course it is Riemann integrable. That is easy to show. And what is the integral? Integral a to b gx dx is in each interval you will get alpha j times the length of that interval, right? That is the Riemann degree, and that you can see is simply alpha j times m of m, remember, is the length of G inverse alpha j. Okay, so G inverse of alpha j is the interval aj to aj plus 1, and you look at the length of that interval, that is aj plus 1 minus aj, and multiply by a value in the range, right, that is alpha j. So this is precisely what happens with the step function, and for step functions this procedure which I defined as Lebeg's idea and Riemann's integral are essentially the same, right? You can see it here, but one has to do this in a much more general setup, because the function need not be a step function always. So if you look at this procedure, the first hurdle you see is that how to define the length of complicated sets, right? So to define length of complicated sets, one needs a good class of sets and a notion of the length which should satisfy various properties. Okay, so let's try to do that. So we need to define length of complicated sets. So if I is an interval, then m of I, that is the length of I, should be the usual length. Okay, so measure of I should be the usual length of the interval. Remember, the interval could be positive, interval could be closed interval, open interval, or one side closed, other side open, and all that, but they all have the same length, right? Because adding one point doesn't really change anything. So an interval AB, whether it is closed, open, its length is B minus A. You want that property to continue to hold, and it is natural to expect that if I have two disjoint intervals, then the length of the union should be the sum of the length of the individual intervals, right? So m of I1 union I2 should be equal to mi1 plus mi2, right, if I1 and I2 are disjoint. Now for analytical reasons we demand a little more. Okay, you will see why this countable additivity, as we call it, is necessary. So countable additivity is, if I have Ij disjoint intervals, so as of now we are still sticking to intervals, then I want the additive property to extend to the union of disjoint intervals, countably many disjoint intervals. Okay, so m of union Ij should be summation Mij. That is called the countable additivity property, and that is very important property of a measure. Okay, so this is what you mean by a countable additive measure, and that is what helps in dealing with limits of integrals. Okay, we will see that. So the class of sets, these are going to be subsets of the real line, where this notion of length is defined is the Lebeg sigma algebra. So I'll define what that is soon. So as I was saying earlier, the length, the notion of the length we require should satisfy, or we need, should satisfy some properties, like disjoint sets should have, when you take the union, the length should add up and so on. So it turns out that it is not possible to define it on all subsets. Okay, so there are various conceptual reasons, technical reasons why this is not possible. I will not get into it, but there is a collection of sets of subsets of the real line where this notion of length can be defined, and we call that Lebeg sigma algebra. So let me define what a sigma algebra is. So let script f be a class of subsets of real line. F is said to be a sigma algebra if, first of all, the empty set, the real line, should be in F. If, second condition, if A is a set in F, script f, then A complement should be there. That means the collection of sets you are looking at is closed under taking complements. And the third one, if Aj are in F, then Aj for j equal to 1, 2, 3 and so on, that is a countably many sets in F, then their union should also be there. Okay. So, there are three conditions: empty set, whole space should be there, it is closed under complementation and closed under countable union. Now, if you, because the complementation is there, if it is closed under countable union, it will be closed under countable intersection as well, right, because if you take the union and take the complement, then you are going to get the intersection. Okay. So, there are lots of things you can do with this complementation and the union. You will get intersections, you can look at A and B and look at A minus B. A minus B is A intersection B complement, that will also be there, and so on. So, most of the set theoretic operations you do, as long as you are doing countably many times, you will still land in your sigma algebra. Okay. So, simplest example is if I take a subset of the real line and simply look at script f to be phi, the empty set, the real line, they should be there, and if I put A, I know A complement should be there, so I put A complement as well, then countable unions, but you know there are only finitely many sets, and you will see that this is the sigma algebra. Okay. So, this is the smallest sigma algebra containing A. Smallest sigma algebra makes sense. Okay. So, intersection of sigma algebras is a sigma algebra. So, smallest sigma algebra will make sense. Now, the smallest sigma algebra containing all open intervals of the real line is called the Borel sigma algebra of R. Okay. So, that is a rather large sigma algebra. You look at all open sets or all open intervals and look at the smallest sigma algebra containing all open intervals. So, you have all open intervals, you take the complement, so you will get all closed sets, then you can take intersections, then you can take unions and so on. Okay. So, it has lots of sets, all of them will be in the Borel sigma algebra, script B of R. Notice that open sets are in BR because any open set in the real line is a countable union of open intervals. So, that will be in BR. So, any closed set will be there because all open sets are there, and BR is closed under complementation. So, closed set is a complement of an open set. So, that will be there, and any interval, for example, a open interval like AB, closed at A, open at B, that is the intersection n equal to 1 to infinity A minus 1 by n comma B open, right. Open sets are there. So, countable intersection of open intervals are there. So, this particular interval AB will be there. Okay. Similarly, singletons are there because singletons are closed sets. Countable union of singletons will be countable sets. Any countable set will be a Borel set or a set in the Borel sigma algebra, like the rationals will be there, and since rationals are there, its complement, which is all irrationals, that will also be a Borel set. Okay. So, B of R is a rather large collection of sets already. Okay. So, it is it's an instructive exercise to write down various sets and see if it is a Borel set or not. Okay. So, let's go further. Now, so we are going to define what is known as outer measure first. This is defined for any subset of the real line. Okay. So, if I take a subset A of the real line, you can define its outer measure. So, outer measure of A by m star of A. So, m star is the notation for outer measure. M star of A equal to infimum over summation j equal to 1 to infinity mod ij, where A is contained in union ij, countably many intervals. Okay. Ij's are all intervals, and mod ij is the length of the interval. So, for intervals there is a notion of length already, right, whatever interval you take. So, ij you should take, well, you can stick to open intervals if you like, it does not really matter. And you look at all the open covers of A, right. A is a subset of the real line. Look at all open covers of A using intervals, sum up those intervals, the length of those intervals. So, that is a good approximation to length of A, right, that is what you will do. But it is possible to cover A with huge intervals, and so A may be very small, but the intervals can be very big, right. That is why you take infimum, so that you cover A very tightly with intervals, and then you look at the length of the intervals, sum them up, and you will get some value, and look at infimum over such collections, right. So, that would be a good approximation for the measure of A, the length of A. Well, we call it outer measure because it is defined for all subsets of the real line. The properties of a measure or a length which we want will be true only for a collection of subsets of the real, not on all subsets. Okay, so that is where the issue is. So one has to find the appropriate collection of subsets where this outer measure will have various properties we want. So that is the collection of Lebesgue measurable sets. So let us define that. A set A contained in R is said to be Lebesgue measurable if m star of E, so remember m star of E is defined for every E, okay, equal to m star of E intersection A plus m star of E intersection A complement. So notice E intersection A and E intersection A complement are disjoint, and you are saying A is so nice so that this disjointification adds up to the total thing every time, right? Whatever E is, this is going to happen. Such a set is called a Lebesgue measurable set. So E is an arbitrary subset of the real line, okay. So clearly A is measurable if and only if A complement is measurable, because the condition m star E equal to m star of E intersection A plus m star of E intersection A complement is invariant under taking A and A complement, right. So they are the same condition. So the collection of Lebesgue measurable sets is already closed under complementation, and it is easy to see that if A is either phi or the real line, this is already true, and so there is nothing to be proved, okay. So the collection of Lebesgue measurable sets is closed under complementation. You have phi and R, and it turns out that the collection is actually a sigma algebra, okay. So the collection of measurable set denoted by L of R is a sigma algebra, and it's a sigma algebra big. So the two properties of the sigma algebra we already saw, right. The empty set and the whole space is there, and it is closed under complementation. So you need to prove that it is closed under countable unions, okay. So that is some work to be done, but such a collection is going to be a sigma algebra. So the Lebesgue measurable set is a sigma algebra, and we have some properties of that, okay. So if you denote it by L of R, then the Borel sigma algebra is contained in the Lebesgue sigma algebra. So remember, the Borel sigma algebra is the smallest sigma algebra containing all open sets, and so Lebesgue sigma algebra will have all open sets, all closed sets, singletons, rationals, irrationals, etc., etc. So it's a huge set. Now second property is if A is a set such that m star of A is 0. So m star of A is 0, meaning you can cover it with very small intervals, right, because you are taking the infimum, and infimum you want to be 0. So you can cover it with very small intervals, and so it is a meager set, right, that is what it means. So if its outer measure is 0, then it is a Lebesgue measurable set. And it is known that if A is a Lebesgue measurable set, then A can be written as B union C, where B is a Borel set and C is a set whose measure is 0. Okay, so between Lebesgue, so if you look at the first property, B of R is contained in L of R, so between them there is not much difference. Okay, so the only sets that gets added to the Borel sigma algebra is those sets whose outer measure is 0, which are very small. Okay, in some sense they are small in some sense, and the Lebesgue measure. So if I take A in L of R, Lebesgue measurable set, then we can define the length called the Lebesgue measure of A to be m of A equal to m star of A, which means that m equal to m star restricted to L of R, right. So it is the outer measure, so restricted to the collection of Lebesgue sigma algebra, that is your Lebesgue measure. Okay, so remember that outer measure is defined for all sets, but that does not have the properties we want. Okay, so that is why we restrict it to a subclass of sets called the Lebesgue measurable sets, which is defined using that condition m star of E equal to m star of E intersection A plus m star of E intersection A complement. That is called the Carathéodory condition. There are other ways of defining it. Okay, so this is one such definition. Okay, now we have the Lebesgue measure, which is coming from the outer measure on the collection of Lebesgue measurable sets, which is defined using Karathi-Odry definition. Now on that collection, M is a countably additive measure. That means M of the empty set is 0. So remember, the outer measure of the empty set is obviously 0, because empty set can be covered with very small intervals, right? And when you take infimum, you will get 0. But the important property that is that it is countably additive, which means if I have A1, A2, etc., An in L of R, Lebesgue measurable sets, and disjoin, then so now you see the AIs are not intervals, okay, they need not be intervals, they are arbitrary measurable sets, and the measure of the union AJ, countable union, is sum of M of AJs. That is the countable additivity property. Okay, so countable additivity is an extremely important property which allows us to take limits and things like that in integrals and so on, which you will see in the next lectures. But let me motivate countable additivity by this picture. So if you look at this region drawn here, how do you define its area? So one way of defining its area is to approximate it with figures which you already know, right? So if you look at a square or a rectangle, you know what its area is. Okay, so you can put a lot of squares or rectangles inside. Of course, that may not fill up the region. So in the remaining region, you will put smaller squares and rectangles, right? You can continue like that and try to approximate this. So the area of all this you can add, but then you may have infinitely many such things, and you want it to add to the area of the whole region. And of course, you can start with bigger squares, smaller squares, different kind of squares, rectangles and so on. Each time you should get the same value, otherwise the area is not well defined, right? So that is precisely what countable additivity is. So it's a, as I said, it's an important property. Okay, so we have a little bit more for the first lecture. Some properties of the measure which allows us to do analysis is, if I have ANs Lebesgue measurable and AN increases to A, what does that mean? ANs are sets, okay. It is increasing, meaning A1 is contained in A2, A2 is contained in A3 and so on. It keeps becoming bigger and bigger. They are all measurable sets. And if A is equal to union AN, so union n equal to 1 to infinity AN, so that contains all the AIs, right. So A is called the limit of AN, increasing limit of AN, like if you have a real sequence, you increasing, you will say supremum is the limit, right. So A is like the supremum of these sets taking the union. Then M of AN increases to M of A. So this is a very nice property to have. Okay, so if I have ANs increasing to A, the length of ANs or the measure of ANs will increase to measure of A. If ANs decrease to A, so that is the second property. If AN decreases to A, that means A1 is bigger than A2 is contains A3 and so on, right. So the sets are becoming smaller. That is what you mean by decreasing, and of course the limit should be simply the intersection of all the ANs, right. So that is A. And so here we have an extra condition, M of A1, the measure of the first one, doesn't have to be the first one, measure of any of them is finite. Then you have the limit, MAN decreases to MA, okay. So this is not true without the finite measure condition. For example, if you look at the intervals n to infinity on the real line, remember that's an interval, so its measure is simply its length, but its length is infinite. So n to infinity has length infinite, but if I take the intersection, that is empty set, and that is, so it has measure 0. But any n to infinity has length infinity, and so infinity is not decreasing to 0. So one of them at least should have finite measure for this result to be true. But for increasing sequences, there is no condition. Okay. Now third property is, if A is countable, then M of A is 0. Well, why is that? M of a singleton is 0. So measure of a singleton is 0 because a singleton, if I take x naught, I can cover it with x naught minus epsilon to x naught plus epsilon. If that is my interval I, its length is 2 epsilon. So, a measure of x naught will be less than 2 epsilon for every epsilon, and so it is 0. And so, if I take countable sets, then measure is 0 because of countable additivity, right. Any countable set is a countable union of singletons. Countable additivity tells me that measure of A will be sum of measure of the singletons, and they are all 0. So, in particular the rationals in the real line has Lebesgue measure 0, even though rationals is dense. Okay. So, it is a big set topologically, but measure theoretically it is a very meager set because it has measure 0. Okay, so that finishes the first lecture, and now in the second lecture we will start with integration, and in the third lecture we will compare Riemann integration and Lebesgue integration and see how how one actually uses Lebesgue integration. Okay, so the next two lectures will be on those topics. Okay, so I will stop here.